Once again, I'm Carringtone Kinyanjui, lead researcher at Haki Artificial Intelligence. I also do some research as a junior research fellow at ILINA. In both these organizations, I am an AI researcher, and in Haki, I am an AI developer. In ILINA, I am an AI safety researcher trying to figure out how to make artificial intelligence systems safe, especially for the African context. Welcome, and I hope you enjoy your class as an introduction to quantum computing. So I am going to start with a little bit of a recap from last week. Specifically, I am interested in discussing the foundations of quantum mechanics, which will then lead us to understanding why quantum computing is a very powerful idea. So the flow of this class is going to be basic. We are going to have a look at the foundations of quantum mechanics and the foundations of computation. And then we are going to introduce quantum computing, okay? And this should take roughly 30 minutes, okay? And after this 30 to 40 minutes, we will have a short break where we will discuss questions from the first part of the class. And then we will go into the advantages and algorithms of quantum computers. Then we will go into the instantiation, how you actually build quantum computers. And then after that, we will focus on the coming decades. What do we expect in the next few decades from these various companies? We won't belabor on that too much. However, we will discuss a little bit of the detail to do with what these companies, these major quantum computing or these major technology companies are planning for the coming years. So let us talk about quantum mechanics a little bit. And I'm sorry for those of you who would rather quickly just get through this difficult part. It is still a very necessary part of understanding why quantum computers could present an advantage in particular problems. So at the top of my slide, there is a particular formulation of the Schrödinger equation that is particularly helpful for quantum computing, okay? So the Schrödinger equation, as we discussed last week, is an energy equation. Why is it an energy equation? It's an energy equation because it tells us stories about the energy of systems and how the energy of these systems is related to their other properties, like mass, like momentum, etc. We said that physics is a study of matter and its relation to energy, and therefore it is necessary to find a way of encoding the behavior of systems through their energy. And the Schrödinger equation is exactly such an equation, especially for quantum mechanics. But we then found out that quantum mechanics has certain weird behaviors that are ascribable to this equation and the terms in this equation. So I'd like you to focus on the thing that is a fork, that is a function of t, meaning that it depends on t. So psi, that is the fork, bracket t, just says that it depends on t. T is time here, because you're looking at systems which are changing with time, otherwise called dynamical systems. This Schrödinger equation applies. Because of the behavior of this thing, and it is called a state vector or a wave function, and it is important for the remainder of our discussion, because of the weird behavior of this equation, it affords certain advantages. It affords certain weirdness that accrue as advantages in quantum mechanics. So we are going to look at some of these. First, we understand that quantum mechanics applies to subatomic or atomic or molecular particles, okay? We have a story for why it applies for the entire universe, but in particular, it is a particularly powerful way of telling stories or describing the behavior of atomic, subatomic systems, okay? There is a difference between the behavior of these systems in these realms to the classical physics that we are taught in high school. One is the measurement effect, okay? So quantum mechanical objects, which are normally called states, remain in a probabilistic sort of spread out manner until you carry out a measurement, okay? So you carry out a measurement, then the quantum mechanical system will collapse into a definite state. And last week, but one, we spoke about why this is particularly difficult for physicists to explain in detail, because physicists have different stories or interpretation about what is going on. Some of the core principles of quantum mechanics that are interesting for quantum computing are superposition, entanglement, and quantum tunneling. Superposition, entanglement, and quantum tunneling. I would like you to note down these big words because they're important for the remainder of our discussion. So just make sure you put these words somewhere: superposition, entanglement, and quantum tunneling. We discussed them in a little bit more detail last week. So superposition. Superposition is the idea that a quantum object, it can be a particle, it can be an atom, it can be anything, can exist in two states that seem to be different at the same time, okay? So it can be either a higher energy level or a lower energy level. It can be something called spin up, or spin down at the same time before measurement, okay? So you can think about a very, very rough idea, hence my picture of this coin that is flipping or spinning, okay? Or flipping in the air. You do not know whether it's going to be heads or tails, okay? When it lands in the ground. So you can say something like it is both heads and tails until it lands on the ground, and then it is a particular face looking up, and then you say it's either heads up or tails up, okay? And this idea that it exists in both states at the same time is what applies for quantum mechanics. However, I'd like to point out that this is not just an analogy. It's not just a way of thinking, right? It's not a frame that you're using to think about problems in quantum mechanics. As far as quantum mechanics is concerned, the two states actually exist. They are not a result of you not understanding the system properly. The two states actually exist, and therefore the particle is in actually energy level 1 and 0. We will speak about the details of quantum computing particularly. This then means that a system, a quantum mechanical bit, otherwise called a qubit, can be either 0 or 1. And we will speak about what this means a few slides down. However, when you measure, when you carry out the measurement, the quantum mechanical system collapses, okay, into one definite state. So you will measure the energy of the electron at being a particular level rather than all levels at once. You will measure the particle being in a certain position rather than a superposition of positions at once, okay? So whenever you're carrying out a measurement, these properties essentially disappear, the property of superposition. And feel free to stop me in case something is not clear. But it is this idea of superposition and the effect of measurement on superposition. Second problem, quantum entanglement. Quantum entanglement. When two particles are linked either because of interaction or interruption, one way or another, right? These particles' properties become shared, and I will explain what this sharing could mean, okay? Such that when you move two particles several kilometers away from each other, and this picture is just an example of what I'm talking about, when you measure one particle, it will affect the other particle instantaneously, or it will imply something about what you're likely to measure in this other particle instantaneously, and vice versa, okay? So it will determine the state of its partner, okay? And this is what Einstein, for you who follow Albert Einstein, have read about Albert Einstein, called spooky action at a distance. Why is it spooky action at a distance? You do not expect physics to behave this way. You do not expect the measurement of one particle in one position to affect another particle in another position. And this is quite problematic. So, entanglement and superposition. These are two things that you should be packing in your mind right now. Superposition, the ability of a particle to appear in multiple states at the same time before being measured, and entanglement, this phenomenon where two particles can be linked in such a way that they appear to be the same state or behave like the same state. Another thing to consider is quantum tunneling, and this will be important for a particular type of quantum computer. Particles essentially are able to cross energy or, sorry, yes, go ahead. Oh, somebody has raised your hand. Go ahead.
Yeah. Before you go to quantum tunneling, now you've said on the measure, back on the quantum entanglement, on the measure of the quantum, is it, what unit do you use to measure maybe the size or the length or that distance, the spooky distance, so per se, like, does it have a particular unit of measurement in terms of size?
Yeah, thank you very much. That's a good question. So essentially in practical experiments, what these people do is that they make sure that the particles interact. This could be a collision or something like that. And then the particle moves the other direction and the particle moves the other direction. And essentially because they're in some sort of, I don't know, it could be anything like, what is this tube? Optical fiber optics, okay? So the particle has moved in that direction, another particle has moved in that direction, okay? You measure properties of this particle, you capture it at a given kilometer, and you capture this other particle at a given kilometer, and then you measure the properties of this side, and you exchange with the other lab partner who is measuring properties on this other side. And you will find that these particles essentially are correlated, okay? And it doesn't have anything to do with the fact that they are supposed to have opposite sides. It has to do with the fact that there's this uncertainty, and this uncertainty implies an entanglement. But essentially what you do is just let the particles move through space and then measure at these ends. And then that will tell you the distance automatically. You will say the particle moved in that direction 1 kilometer, and in this direction 1 kilometer. Therefore, these two particles were 2 kilometers apart, something like that. I hope I've answered your question.
Awesome. That's good. That's well answered. Thank you.
Okay, thank you. So yes, quantum tunneling, back to quantum tunneling. It's this idea that essentially you have an energy barrier, and this energy barrier, typically, if you throw a ball on the wall, you do not expect so-called magic. You do not expect the ball to go through the wall. It will bounce. If you throw it 100 times, it will bounce 100 times back, okay? And a lot of football depends on this idea that the ball will be captured by the net, okay? or will be captured somehow. So imagine if you're able to shoot that ball to that goalpost, and then the ball always went through, even when it hits the post, it goes through the post. It will be a very weird thing. Or you're trying to kick the ball, and the ball essentially goes through your leg, or your leg goes through the ball. This would make it very, very difficult to live our lives, right? I'm sitting on a chair. Imagine I was able to like go through the chair. I will just fall down immediately and maybe fall through the floor and get to the first floor, etc. It will be a dangerous life, in short. So this is essentially what happens in quantum mechanics, right? For a small probability of particles. Most of the particles are not going to be able to penetrate the energy barrier or the wall, right? A wall is a type of an energy barrier, right? Meaning that you need certain amount of energy to get through the wall, to punch through the wall, right? But for particles, even for particles that have lower energy than the energy you need to force your way through the wall, some quantum particles can get through. And this is an example of that in the picture, okay? We do not understand the fundamental physics for why this is the case, but the phenomenon has been observed, okay? There are different theories for why this is the case, but the phenomenon is quite clear and quite experimental. And there is a possibility that you can even carry out this experiment, I don't know, in the University of Nairobi, in Makerere, etc. The tools, the instruments you need to carry out this experiment are not very complicated. Now, these will become important for a specific kind of quantum computer we will discuss called a superconducting qubit, okay? And superconducting qubit quantum computers, we will discuss this in a little bit more detail in the coming slides. However, just pay attention to the idea that particles can move through energy barriers. Now, we are done with the three ideas of quantum mechanics that you need to have absorbed for you to understand the rest of the things I'm going to talk about. One is superposition. Second is entanglement. Third is quantum tunneling. Superposition, entanglement, and quantum tunneling. So we will move to computing. We spoke a little bit about computing last week. We said computing is the process you use to take advantage of a machine to carry out arbitrary computations for you, okay? Computing is this idea that you can take a pile of bricks. This is the example I used and the example that I like using. You can take a pile of bricks and pile it up into anything. You can pile it up into a pyramid. You can pile it up into a formless heap. You can pile them up into a house, a hospital, a church, an office, a school. Okay? And the things you're piling up when you're doing computing are called bits. Okay? And bits are just zeros and ones that you can combine in several ways to do several forms of calculation. And then these calculations can then be mapped into computations, okay? So if you're able to represent anything as a number, and you know because of encoding that you are able to represent anything as a number, right? This is the process of encoding. You're able to compute that number. You're able to calculate that number. And the process of calculating the encoding of these numbers is the process you call computation. And the things, the bricks that you use to carry out this calculation, or the stones that you use to carry out this calculation, are called bits. Now, using bits at their level is difficult, so you need to have something called a logic gate. A logic gate tells you how two bits are related to each other. When these two bits meet, right, under this logic gate, what are we supposed to find as the result, okay? So it is a form of arranging bits in a logical manner, in a manner that makes sense. Because most probably, you don't want a heap of numbers. What you want is a good arrangement. For example, a good arrangement of bricks in the form of a square, okay? So that you have 4 walls, and then you can put something on top of the wall and call that thing a house, a hospital, a clinic, okay? So similarly, the logic gates are the things that you use basically to make sure that these bits are related to each other in a good pattern, in a stable pattern, so that you can be able to carry out arbitrary computations on top of these logic gates. You combine logic gates using something called an algorithm. Now, I'm sure you have heard of algorithms, particularly those of you who are Kenyans, right? Algorithms and IBC, right? The algorithm was doing this, the algorithm was doing that. An algorithm is a set of instructions that you give to a computer on how to arrange its logical flow. That is how to arrange its logic gates to perform a certain computation for you. So the principle is very simple. You have bricks, okay, called bits, okay, binary digits, 0 and 1. You arrange these things into logic gates, okay? The logic gates will specify how the bricks should be arranged in a legal manner, in a manner that makes sense. And then these things are going to then be used to build your house, your arbitrary computation. And arbitrary computation can mean the presentation of slides. Arbitrary computation can mean Zoom. Arbitrary computation can mean calculating 55 times 76, okay? All these are arbitrary forms of computation that can be realized by these very simple logic gates. Examples of this are and, or, and not. Now, how do you know that this system that you have built very, very simply, how do you know that your bricks can build any acceptable house? Okay? How do you prove that? You prove that using something called a Turing machine, which tells you that given a machine of extensible memory, so this is infinite memory this way, and infinite tape the other direction, right? It can carry out any arbitrary computation. And this is called a Turing machine, okay? And now it tells you what kinds of algorithms you can carry out inside your computer. So your computer is an example of a Turing machine. Now, so what is the story here? I have something that is either a 0 or 1. And I am going to specify how these zeros and ones relate to each other through the logic gates, through the walls, right? My square wall or my round wall, it doesn't matter. But I specify the pattern in which I'm going to relate these bits. And then using that, I can build a computer that can carry out any computation that I would like to do. So this is the principle. And this is the principle of classical computing. However, let's go back to quantum mechanics. We have said we can have a system that exists in both states at the same time. So the question is, can I use this thing, the fact that this system, this quantum bit, can exist in both states at the same time to carry out an arbitrary computation? That is, instead of using these zeros and ones, which actually are just voltages in a circuit, high voltage 1, low voltage 0, can I use a quantum system to simulate the process of computation? Does the fact that it exists at two places at the same time introduce a complication, or does it introduce new possibilities? And this is the question that people called quantum information theorists asked in the 70s and 80s and the 90s too. So they created something called a quantum bit, okay? And the quantum bit is essentially the analog, the quantum mechanical analog of the normal 0 or 1. That is all that it is. It is the quantum mechanical analog of the 0 and 1, with the added possibility that it can exist in both states of 0 and 1 at the same time. Okay? So what are the differences here? This is the chief difference. One, a classical bit is either 0 or 1 and nothing in between, or no combination of the two. Okay? So it's either 0 and 1. And the classical bits are the things inside your laptops. Okay? So those are classical bits. A quantum mechanical bit, a qubit, can be both 0 and 1. And it exists actually in a superposition at the same time. And it will enable certain things we call quantum parallelism, which I will explain in a moment, right? And exponential information density. Don't worry about the big words. We will talk about them in a moment. Another thing about logical gates, okay? So the classical logic gates, these ones that I've just spoken about. One, they're irreversible, irreversible. So if you take a 0 and a 1 and put them through something called an AND gate, okay? It will only say 1 on the other end if both these are 1, otherwise 0. Okay, so it's a logical operation. It will take these two data, 0 and 1. If both of them are 1, say 1. If both of them are not 1, say 0. Okay, so it says 0. So this is the fact that they're irreversible. I can't start from the result here and tell you what was on this other side. And therefore, logical operations on your computer go only one direction. And this is one of the fundamental reasons why it is very difficult to recover data that you have permanently deleted, okay? Although it's possible, you can do some weird things. And nowadays there's extra engineering that you can play around with things and recover your data. But most of the time, it is very, very difficult to do. And in some cases, for older machines, it is impossible to recover your data, especially if you overwrite your data. Because logic gate operations are irreversible. And then they're based on Boolean logic. Boolean logic is this idea of 0 and 1. Boolean logic is otherwise called binary logic. So it is this idea of 0 and 1, okay? So true or false, that is an example of Boolean logic. Statements are either true or false, okay? And therefore you can construct an entire so-called logical system on the basis of this. And then information can be lost. Why? Because you have irreversible operation. So if you carry out a deletion operation, if you carry out an overwrite operation on top of your machine, if you format it, or if you do something with it, this information can be lost in a very, very fundamental sense. You have essentially completely destroyed your bricks, okay? You have smashed through your bricks. So that house does not exist anymore. It has gone. And this is essentially a deletion operation. However, quantum gates, which are constructed from quantum bits, are a little bit weirder. Okay, so similarly, it has been found that you can arrange quantum bits, okay, in such a manner that you can carry out logical operations on them, and this will become quantum logic gates. So one, they are reversible, and this will be important. They are reversible, so they can go in both directions. You can move information in quantum mechanics this way, and you can move it back this way. Logical operations in the classical sense do not operate this way. Second, they preserve information, especially so-called unitary operations. Don't worry about that. It's a quantum mechanical thing. Don't worry about it at all. But the idea is that quantum mechanical operations on logic gates, on quantum systems, preserve information throughout. And that is why they're reversible. You can tell that it moved from A, changed to B, C, D, G, H, okay? So I can then work back and go back exactly like that and reverse my logical operation. And therefore, they also enable something called quantum interference. Because they can exist in two states at the same time, they allow this possibility that an extra system can interfere with the property. 0 and 1 do not fundamentally interact. We only systematize how they interact through logic gates, but they don't fundamentally interact. They can't be mixed with each other. However, quantum logic gates can allow quantum bits to interact. I want to mention two special quantum logic gates. There are several. I don't want to get into the details of this. We will probably do much more detailed discussion of this in the workshops in October as Quantum Kenya. But just to mention two quick ones, there's one called the Pauli X, which is a quantum NOT gate. A NOT gate in the classical sense just takes a 0 and says not 0. So what is not 0? What is something that is not 0? It is 1. This is the other bit that you have. What is something that is not 1? It is 0. So a NOT gate flips a classical logic gate, and therefore you have a similar system in quantum logic gates. And then another example is the Hadamard gate. The Hadamard gate is important for quantum mechanics, Hadamard, Hadamard. It's important because it creates this magic. It creates superposed states, states that can exist in two or more positions at the same time. And you will see why this is important. So again, you're playing this game of computation. Instead of bricks, you are using quantum stones to build your quantum computational process, okay? And later on, your quantum computer. So you're not using bricks, you're using stones. Stones will give you certain advantages, not all the time, because it still makes sense to live in a brick house. Nonetheless, there are certain things stones can do that bricks cannot do, okay? The stones of quantum computing can do some things that bricks cannot do. But however, stones are still very expensive. So if you can construct things using bricks, you do it. But if you need to use stones to build your house, you do it. So this is the idea. But both ways, you're building a house. You're building something to live in. You're doing forms of computation. So you take your bricks and your stones, right? On the left, what you do is build logic gates. On the right, what you do is build quantum logic gates. And then you carry out arbitrary computations on this material. Now, I want us to discuss a little bit about quantum parallelism. And I would like to start with a story of puzzles. So you have a puzzle, right? This usual, if I can quickly share an example of a puzzle. Or a maze. Let me share a quick image of a maze, just a moment. Just a moment as I share my picture. Okay, so that is a maze. Can you see that nice green maze over there? Please confirm by if you can see.
Yes, we can.
Okay, thank you. So you have this maze and you want to navigate it. And this is usually a test of your spatial intelligence or spatial memory or a combination of both. So you start at the center and you try to find your way out. The center is somewhere there, you can see, and the place where the exit is up there. You can say to the north of the picture, essentially. But I'm not sure that's geographical north, but anyway, it doesn't matter. So you can use the sun to tell geographical north. Anyway, that is your exit. If you are an individual, you would need to try out several possible paths, several possible junctions, and then you will slowly find your way outside, okay? Although you will take time. However, imagine you are not like a human being. You are something more ethereal, something like water, okay? So if I put bucket loads of water, if I pump a lot of water through this system, okay, and we assume the flow is like solid and all these other things, so such that the water is forced to flow through the paths, the water will not take very long for the first drops of it to come out of the exit. Why? Because the water is able to explore all these paths at the same time. And if this thing is vertical, essentially all of the water will eventually find its way outside the system very, very fast. So the water will solve the maze faster than a single human being or a single mouse or a single dog will be able to do. Why? Because it is exploring all paths relatively fast, okay? So a bit of that water moves in left, a bit of that water moves right, a bit of that water moves up, a bit of that water moves down, etc., 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 until in no time, the gallons of water are able to get out of the exit. And this is an important idea called parallelism. If you have a difficult problem, exploring all possible solutions at the same time reduces significantly the time you take to solve that problem. So if I have 3 times 3 and I can test whether 3 times 3 is 4, 5, 6, 7, 8, 9, 10, 11, at the same time, it makes it quite easy for me to find the answer that 3 times 3 is 9. Okay, and this is an important problem as we discussed last week called search. So let me go back to sharing my screen. Just a moment, my slides. Back to, no, these are not my slides, just a moment. Let me find my slides, there they are. Okay. I hope you can see my slides. So this process for quantum mechanics is what is called quantum parallelism. Quantum parallelism. And I'm sorry for the big words, but quantum parallelism is that idea that quantum mechanics essentially allows quantum systems to be like water, okay? Such that they can be in several states at the same time. You can never say that the Indian Ocean is at this position. The Indian Ocean is both near Kenya and Tanzania and India at the same time. The Indian Ocean is a huge mass of water. So it is near India, near China, near Somalia, near Kenya, near Tanzania, near Mozambique at the same time, okay? So similarly, quantum systems can be in multiple states at the same time, like water, and they can explore possible solutions to a problem several times at the same time, okay? Quantum parallelism also allows a very interesting idea called the compression of information, okay? So if you have 2 qubits, 2 qubits can represent 4 states. And you can tell how many qubits you need to represent, how many classical bits you need to represent 4 states. So you have 0, 0, okay? 0, 1, 0, 1, 1, 0, and 1, 1. So again, I repeat, 0, 0, 0, 1, 1, 0, and 1, 1. So you need 4 bits to represent, you need 8 bits to represent, you need 4 bits to represent 4 states. However, you need 2 qubits to represent the 4 states. Why? A qubit can exist in 2 states at the same time. By the time you get to 10, just 10 qubits, you are able to store the information of 1024 states at the same time. So just 10 things can store the information of 1000 things at the same time, okay? So if you are able to build a flash disk using qubits, it would be amazing. It would be amazing. So a 1 MB flash disk can essentially, if I guess well, store the entire internet, okay? A 1 MB qubit flash disk. So 300 qubits, this is enough to store more atoms than the universe. It is enough to store all the information of the universe. So I hope you can see this massive scale up compared to the behavior of classical bits. So if you are able to store multiple states in a very small amount of thing, you are able to explore all of these states using this small amount of things. I will give an example. If I am able to store enough water to go through my maze in a tank, it means I can use that water in that tank to essentially understand that maze, to solve that maze, okay? And therefore that tank is best for me. However, if I used human beings, I might need to use, I don't know, 100 or 50 so that I'm able to like go through the paths all the time. And therefore, this allows qubits to explore multiple possible states at the same time. And these multiple possible states could be, for example, multiple possible answers to a question. And if multiple possible answers to a question can be explored simultaneously, it implies you can do very, very rapid speed ups in calculation. And this is what we are going to discuss a little bit. So I think I am halfway. Let me just confirm using the number of slides. Yes, I am halfway. So we will stop a little bit for 10 minutes and then go back to the remainder of the slides. So any questions up to there? Any questions? Any questions? You can now go for coffee and wonder what I've just spoken about. Any questions? Please raise your hand. Any clarifications? This is very confusing information because it is a very confusing subject the first time you interact with it. So there are no like stupid questions. So please ask your questions so that we clarify things for everybody else. Yes, go ahead. Go ahead. PLP.
Okay, thank you. So my question is now, since we can be able like to use quantum qubits for better spacing and better memory, how actual is it? Can we be able to actualize it like when you are making a physical RAM? We, instead of making a 10 GB RAM, we use 1 MB RAM that works the magic of what can be done with 1 TB RAM size.
Can you please tell me your name? I know that you're here, you're using your company. or
Yeah.
your organization. What is your name?
My name is Chakin.
Jakin.
Yeah, Chakin.
Okay. And people, please feel free to introduce yourself so that we can create a network here. Okay. Thank you, Jakin. This is an interesting question. This is why I was asking your name. And essentially, it will be answered by the remainder of the slides. So you have a very good theoretical idea that these systems can represent a lot of information using very few physical states. And what this tells you is that they're able to compress information much more effectively than any zip file you're ever going to make in your life. Now, however, there's a lot of engineering that comes with this theoretical idea. So the first simple question you can ask yourself is, how can I actually build an actual quantum bit? What material do I need to use to build an actual quantum bit? And very soon, you start to realize that there's a lot of complication, okay? First, you need to keep these systems isolated. There's a problem we will talk about, which complicates issues. Second, you need to keep these systems from interacting with each other, which is another complication. And very, very fast, you realize you cannot create a mass storage device this way. So you need to find other things to do. Or if you decide to really go down this path, there's a lot of engineering considerations that you need to take into account. So we will discuss all of these intricacies in a moment. Thank you. That was a very good question. Another question, if you're feeling shy or you're in some place where you can't ask a question, please free to pop it in the chat, sorry, and then put it in the chat and then I can have a look. Yes, Enoch, I can see a question. I would like to know how we interact with these qubits, or are they in a theoretical phase? Good question, Enoch. Sorry, I'm muting myself unnecessarily. But no, Enoch, they're not theoretical, they are practical. We will speak about specific instantiations of this created by Microsoft, Google, SpinQ, and other quantum computing companies. They're not just doing quantum computing, but here we are interested in their quantum computing projects. So for this reason, there are actual things that you can interact with. And especially in the case of IBM, you can even sign up to rent a small quantum computer for a short amount of time. And this will probably be discussed in later lessons where you can actually interact with these quantum bits. You can use them to perform basic computations. And we will explain why I have added basic, I have underlined basic in my answer, just in a moment. Okay, thank you, Enoch. That was a good question. Kevin, hi, Ogeto. Is there a deep structural analogy between how the principle of least action employs path integral formulations to select stationary trajectories, and how quantum parallelism uses interference to amplify correct computational paths? Do optimization principles from physics like least action offer insights for designing efficient quantum algorithms? Okay, Ogeto, that is a complicated question first. I will explain a little bit what the principle of least action is to the rest of the class so that we can be on the same page and see why they are helpful. They could be helpful for what you're talking about, although I'm not aware of somebody specifically doing that for reasons that I will explain. So one, what is the principle of least action? There is a very, very good book I'd like to share quickly. Called the lazy universe. So this is the book. If somebody is very, very interested in physics, you can have a look, okay? The principle of least action is this idea that the universe does not like spending energy unnecessarily. So it will choose the path, whichever path, that most conserves energy. A practical example of the principle of least action is that it is easier to go up a hill in a spiral manner where the slope is gentle than to go up a hill directly like this. You use more energy when traveling up a hill in a straight line than you do traveling, moving around the hill like that. And similarly for very many other things. It is this idea that you should choose the path that least expends your energy. So when someone asks you why you're lazy, say I'm lazy because the universe is lazy, okay? You're trying to conserve energy. The least amount of energy spent in a dynamical system satisfies the principle of least action. So that is it, first. Now, there is a particular interpretation or a particular formulation rather. Well, it is a little bit of both. I will explain the difference between the two of quantum mechanics that works on the principle of least action. It tells you that given a set of particles moving in that direction, I can use this idea that the universe is lazy to calculate the likely trajectories of atoms or particles through this given space, okay? So this is called the principle of least action applied to quantum mechanics. And particularly, I will put this in the chat bot. Somebody interesting to look at is called Feynman. Feynman constructed a formulation of quantum mechanics on the basis of the principle of least action called the path integral approach. It tells you that given a set of possible trajectories, the universe will select the most likely trajectory as the simplest. So some simple straight curve like that, okay? It is not universal, but it is likely that the universe will select this path. Now, Ogeto is asking whether this is useful for optimization in a computer. And you can see why it could be useful. You have a set of possible paths, and essentially you write your equations in such a manner that it uses the principle of least action. So it chooses the simplest path. And if the simplest path coincides with the answer of your problem, then it is a solution. So that is the principle, okay? Now, my answer to Kevin is this, and I could be wrong. So this is an opportunity for people to get into Google and ChatGPT, etc. ChatGPT is a much more knowledgeable quantum physicist than I am, and I'm just a student of quantum physics. My answer for your question is that probably no, because the formulation of quantum mechanics, this particular way of looking at quantum mechanics, does not fundamentally alter the understanding of quantum mechanics, okay? So a quantum engineer that is using the so-called matrix formulation or the wave mechanical formulation, the wave mechanical formulation for the people in the class is Schrodinger's equation, essentially. Somebody who is using that will arrive at the same answer because of the behavior of quantum mechanical systems. So I do not see an automatic connection between me carrying out this optimization using PLA and path integrals and automatically proving certain fundamental quantum properties, because I can do the same essentially using any other formulation of quantum mechanics, although it might be more involving. So, however, I will go and check that I am wrong. There's probably some paper outside there saying that you can do exactly the thing that I'm saying is not useful. So I'll go and check. Thank you, Ogeto. That's a very good question. Koskei. Thank you, Koskei. What makes a qubit fundamentally different from a classical bit, and how do superposition and entanglement give quantum computers their potential advantage over classical ones? So, Koskei, this has been essentially the point of my first 10 slides. So, what makes qubits fundamentally different from classical bits? Their ability to exist in multiple states at the same time. And the ability to exist in multiple states at the same time allows compressions that classical bits cannot carry out. Compressions not only in space, right? For those of you who do computer science, this is called space complexity, memory, but also compressions in time. That is time complexity compressions. That means that they are able to carry out computations much, much faster than classical bits. How do superposition and entanglement give quantum computers their potential advantage? Superposition we have already spoken of. So it compresses the amount of physical stuff that you need to carry out a computation. And storage is a form of computation. That is another way of looking at it, right? So it reduces the amount of physical stuff that you need to carry out a computation. And therefore, pound for pound, if you have a kilogram, this is not a very good measure of computational units, but if you have a kilogram of quantum bits and you have a kilogram of classical bits, the quantum bits will be able to do much, much more, much, much faster than the kilogram of classical bits. Yeah. Ogeto has a follow-up question before we get into now the second part of the slides. I'm also wondering whether your own intuitions regarding your study, particularly the epistemological foundation of quantum physics, computing, leads you to the idea of an undiscovered unifying principle. Now, the question of quantum gravity, Ogeto remind me at the end of the presentation, because I don't want to confuse people, but that is a very good question. And essentially my answer is yes, because we are making the claim that quantum mechanics is a universal model, and therefore gravity can be subjected to it as all other forces and phenomena, and therefore, in principle, we should be able to write equations that describe the entire universe using quantum mechanics, and therefore there's an element of what you can call quantum universality. But please ask me again so that we can flesh it out towards the end. Enoch, if qubits have the ability of changing their attributes or properties, how do you identify these changes when comparing different qubits? Enoch, that is a good question that will be answered by our third or fourth last slide. So let us go back to the slides. So from the questions I'm seeing here, people are starting to pick up the salient points, okay? These are very good questions. People are starting to pick up the salient points of quantum computing. Oh, Ogeto, back to you. I forgot that there was this like massive thing called quantum information theory that wants to particularly ardent, particularly fanatical physicists who are there to quantum information theory want to recast everything in the universe as a form of quantum computation, okay? It's a very interesting field. It is these people who speak about it from qubit, that is meaning it, a substance, coming from qubit information. So stuff, matter, energy, etc. comes from qubits. But this is theoretical stuff that I don't want to get into right now. Okay, let's go back to the slides. Just a moment. In case you have any questions, please save them up for the end of the presentation. We can do another basically 20 minutes, 30 minutes at most, and then we'll be able to get into more detailed questions, ways forward, etc. Okay, we have our quantum stones. We have our quantum squares, okay? Just like we said, we have bricks, and then we can build walls out of those bricks and houses out of those walls. We have our quantum walls. Can you hear me? Confirm that you can hear me. Okay, I think you can hear me.
Yes, we can.
Thank you. Yeah, thank you. So you have quantum walls, you have quantum stones, you use them to assemble quantum walls using these quantum logic gates, and now you want to carry out computation. And then you have seen that these systems can represent a lot of information in very small things and can carry out a lot of computations, therefore, in very small numbers. And now you want to take advantage of this. So we will speak about software and logic, and then we will speak about a little bit about engineering, okay? So first, how do you create so-called quantum software, quantum computing software? These are the algorithms. You remember algorithms? Algorithms are the things that we use to arrange logic gates so that we can come up with with any computation, any acceptable computation that we would like to carry out. So similarly, quantum logic gates can be assembled into quantum algorithms, which can therefore show forms of quantum computation. So you are doing essentially the same process. It is only that you're using weird things down here. Okay, quantum interference. Now, you want to find out ways for which you will find your answer, okay? Essentially, I am trying to find my way through this maze, this very, very complicated maze. I'm trying to walk through this maze, okay? How do I direct, quote unquote, my water so that it essentially finds its way to the exit? And all sort of water will follow it into the exit. This is a very, very difficult and interesting problem in quantum computing called amplitude engineering, okay? Now, we spoke about, I want to, it was in my previous slides, it was in my quantum mechanics slides. We spoke, but I can use this picture essentially to explain it. We spoke about waves and how waves cancel each other out or add each other up. So if you find two waves that are in phase, that is, they're going in exactly the same way, like that. So this is one wave, and this is another wave, and they're going in exactly the same way, like that. You can do something called constructive interference, where the amplitude of this wave will add up with the amplitude of this wave, and you will have a bigger amplitude like that. The amplitude is the distance between the 0 point of a wave or its base and its height, okay? So this is how, for example, sound amplification occurs. They take two waveforms, put them together, the amplitude becomes high, and therefore my voice becomes loud. And this is what is happening in your devices. There's another phenomenon where the things are out of sync. So they're moving like that. Hey, I don't even know how to do it properly. Like that. I don't know how to do it properly. Like that in a circle. Like that. Like that. Yes. So they are out of sync. This wave is opposite of this wave. When they meet, they do something called destructive interference. So this is how, for example, you can turn signal into noise. You cancel out the signal, and then you have So that's destructive interference. So for green and orange waves, in places where they're in sync, you will get constructive interference, and that has been pointed in the arrow. And in places where they're out of sync, you will get destructive interference, the flat surface that you're seeing. So because we said that quantum mechanics works on the basis of this big fork, and this big fork is something called a state vector or a wave function, underlying wave, we can essentially find ways of inducing this state vector or this wave function to destructively or constructively interact with itself or other systems such that it can find an answer where it constructively interferes, okay? It shows this amplitude where there is an answer. And if you set up your problem in such a manner, it is very, very easy for the state vector to find out where you want it to constructively interfere. So you turn from being a quantum physicist into a quantum engineer. So you're finding ways of engineering natural properties, and this is what all engineers do. Take advantage of natural properties of the universe or the world to create certain technologies. In this case, we are taking advantage of the fact that the wave function describes wave-like properties, like, for example, quantum tunneling, or, for example, quantum superposition. We are saying that, fine, this is a wave. We are not going to philosophize too much about that. What we are going to do is do engineering and take advantage of these constructive and destructive interferences and essentially find a solution. And this is the important piece of quantum mechanics. So what you want is that your constructive interference positions essentially end up as your solutions to your particular problem. There are multiple possible answers. You want to write an algorithm of telling the quantum system to destructively interfere where there are wrong answers and constructively interfere where there are correct answers. If you're doing optimization, you want it to destructively interfere where there are suboptimal answers and constructively interfere where there are optimal answers. So you need to be a software engineer, a quantum software engineer. What does a software engineer do? The most important thing about a software engineer is not the fact that they can write fluent Python, they can write fluent Java, they can write fluent JavaScript, the document object model, blah, blah, blah. The most interesting thing about software engineers is that they're able to break up a complex problem into small steps such that they can tell the computer to solve each of these small steps iteratively or step by step, and then find a solution, i.e., software engineers can think logically. So how do you become a quantum software engineer? You do the same thing for quantum computing. Just the same way you think about abstract problems, you break them down, and then you write the code, right, that follows the logic that you have thought about, okay? So the code is incidental. And this is why people are saying maybe AI will not be able to fully replace software engineers. I disagree. But anyway, the idea is that you're able to break down problems logically, i.e., you're able to construct these algorithms, these walls that you will use to carry out your computation. So the first algorithm we will look at that is quantum mechanical in nature, or at least shows that given this algorithm, a quantum computer performs much better than a classical computer, is Shor's algorithm, S-H-O-R, Peter Shor. And then his algorithm is called Shor's algorithm. It's a very, very simple thing. The idea is to, given a number, and a specific type of number called a semi-prime number. A semi-prime number, don't worry about this too much, is a number that is the product of two prime numbers. So 3 times 5 is equals to 15. 3 is a prime number, 5 is a prime number, 15 is a semi-prime number, okay? So given such a number, can I find the prime numbers, which if I multiply them, I will be able to find this semi-prime number, okay? So this becomes very, very complicated for very, very large numbers. For example, if I told you to find me the prime numbers that if I multiply them, I get 119, you will take a bit of time to find out that number, okay? However, I think these are 7 and 17, confirm. However, because it takes a lot of time to find these numbers, these prime numbers that you multiply to find this big prime number, this big semi-prime number, essentially a lot of the security of your world, your digital world, rests on this idea that if I have a number that is, I don't know, 10, 20, 30 digits long, that is a number that I need to find the prime factors, the prime numbers that I can multiply to find it, I will take a lot of time. And you can prove that it will take something like, I don't know, more than the age of the universe to find this solution. So therefore, it will take somebody more than the age of the universe to get into your WhatsApp, okay? This is the idea for classical computing. So Peter Shor in 1994 showed that you can build an algorithm that allows quantum computers to do this in hours or days. Okay, so if I wanted to get into your WhatsApp chats, I need a quantum computer and I need maybe hours or days to do this. How does it do this? By efficiently factoring these numbers, and then it will break your encryption and therefore break your code and then be able to access this, okay? And this is why people think that it is a cryptographic threat. It threatens particularly these reversed Shamir-Adleman encryption, RSA encryption, which protects a lot of the internet, okay? It does this by doing something called a quantum Fourier transform. Essentially, it is this idea, the same idea that we are talking about, constructive and destructive interference, but essentially it uses waves, right? We are back to waves, to find out the minima, certain minima, and these minima are essentially candidates for prime numbers. And then you continue this process, you test, you fail, you correct the system, you continue this process, and then you find again the minima, and you end up finding the perfect prime numbers that you need. So this is one algorithm for which it has been proven that quantum computers are advantageous in. The second kind of algorithm is called Grover. We spoke a little bit about it alongside Shor, but we will speak about it right now in a little bit more detail. Grover's algorithm is essentially trying to apply quantum advantages, right, for problems of search, okay? So you have some unsorted database, okay? So it has 1 million numbers. Excuse me, these numbers are not in order. So it is 300,000, 455,625, 97,256, 25,000. So it is not sorted, okay? It's not in order. Now you want to find a specific number here. What classical algorithms do is split this database in two, search here, split again in two, search here, search here, search here, and then roll out all these small halves until they get the number you're looking for, okay? And they do this by trying to sort the system first, and then basically finding your number will be a basic lookup, okay? It will just go and find the 500th number, and that number will be 500 or 501, depending on where you start. Now, Grover's algorithm is a little bit interesting. So this process of just doing that scales quadratically with the size, okay? It gets more complicated the more stuff you have. If you have 100,000 letters to sort, some of you were not there when we were sending letters. I'm sorry for you. If you have 100,000 letters to sort, okay, having a million complicates the amount of work you do by that amount, by as much amount, by 6 times at least. However, Grover's algorithm allows you to do it in the square root of the size, okay? So it does not get more complicated very fast as you get bigger and bigger data sizes. It allows very, very quick search. And it has been found that essentially what this means is that it offers 50% speed up from classical algorithms. If you take 10 days to sort data, it will take you 5 days. If you take 5 hours to sort data when you're doing your programming, it should take you 2.5 hours. And what this means, there are specific forms of algorithms called SHA. And for those Kenyans, those of you who are Kenyans, I don't want to trigger you, but this is secure hash algorithms. Essentially, how do you secure certain objects in the internet, cryptographic objects? You can ask me the details. But essentially what this does is reduce the security of these objects by half. So there's something called SHA-256, okay? It reduces the complexity of solving this problem by half, such that SHA-256 has the same security as a much weaker system called SHA-128, okay? And therefore it weakens certain kinds of cryptography too. But it also optimizes search and sort, which is powerful. There are other quantum algorithms that we will not get into in detail unless you ask me questions and stuff. There are simulation algorithms. So quantum mechanics is good at simulating quantum mechanics, okay? You need much more information to simulate a quantum system using a classical system than you need to simulate a quantum system using another quantum system. And therefore, you can create algorithms which optimize this simulation, okay? And IBM is carrying out a lot of this research with other companies. There's something that is coming up. It is not clear that it is going to perform much better than classical learning algorithms, but there's something coming up called quantum machine learning or quantum artificial intelligence or quantum deep learning, whatever you decide to call it. Basically, the idea is to optimize the training, optimize how you carry out pattern recognition, and the idea is you can build training algorithms, machine learning algorithms that can allow you to do rapid speed ups or rapid optimization. Now, these results are largely theoretical. So people are writing like very deep mathematical papers for why this is the case. It has not been proven very strongly as far as I know. And even in the Indaba last month, there was a lot of discussion on quantum machine learning. But essentially, this is literally in its birth stages, if you will. But there are other optimizations problems like complex scheduling. Complex scheduling is essentially this Grover search. You want to schedule, for example, I don't know, this is a very simple example. You are about to meet 1,000 people. You are the president of some country. You can think about, given what these people want from you, you can reduce this problem into a scheduling problem. I should meet this one who will give me information which will be useful for meeting C and E and F. And this one can come later on because it will only be useful for meeting Z. So you can find ways of optimizing this, or even routing now, or routing, sending massive amounts of Jumia packages to massive amounts of customers, and even resource allocation challenges, okay? So all these logistical problems are useful or can be demonstrated to be optimizable by quantum computers. Now, we have spoken about software, okay? We have spoken about the basic units of computation. The classical bit, the quantum bit. Why the quantum bit has higher capacity than the classical bit? We have spoken about why the quantum walls, the quantum logic gates, are powerful compared to the classical gates. That is, they are reversible, okay? They store information indefinitely because you cannot destroy information in quantum mechanics. We have spoken about parallelism. Parallelism in storage, parallelism in computation, and why the ability to represent multiple states of information using small amount of bits, of qubits, is advantageous. Advantageous in storage and advantageous in computation. We have spoken about specific software that you can construct and ways in which you can construct software, right? You can do quantum software engineering. Specific ways you can build software such that quantum bits, quantum algorithms, quantum gates are advantageous. We have called these quantum algorithms. We have given two classical examples, Shor's algorithm and Grover's algorithm. But we have noted that there are others. Now, that is the software. That is, those are your classical, those are your bits, sorry. Those are your algorithms. Those are your JavaScripts, etc. Now, how do we build the hardware that we will integrate with the software so that we have a full-on quantum computer and we have a complete quantum computing process, okay? So we have spoken about software and all looks nice and interesting. Now we have to hit the road running. The first way you can do it is using things called superconducting qubits. And I'll explain. A conductor is anything that can pass electricity. This is from, I don't know, from 2 physics or something. Now, a superconductor is a specific kind of material that allows electricity to pass through it without any interference, without any resistance. So the electrons just they just pass, okay, with little and I think actually no resistance. And this is efficient. Why this is efficient? It allows the amplitude. It allows you to work with even 5 electrons, okay? Because you're able to detect that very, very small current. And the fact that you can get to those very, very small currents mean that you have to start taking into account quantum mechanics. Now, there's something called a Josephson junction. And the Josephson junction is very simple. You take a conductor and another conductor and you put a non-conductor between the two. Now, in the case of quantum mechanics, we have just spoken about this ghost here. This ghost called quantum tunneling. We have said, even if you put a barrier, there is a possibility that an electron can pass through that barrier. So therefore, when you do the same thing with Josephson, right? This idea that you can put an insulator, let me try and find ways of demonstrating it. I hope things don't fall. So this is your Josephson, this is your insulator. These are your two conductors, okay? So you take your conductor, put an insulator there, and take another conductor, put it right next there, okay? So that's the idea. Now, we have...
Are you
sorry?
demonstrating something? Are you
Yes.
demonstrating something we can't see?
Yes. Oh, sorry. Let me stop. Let me stop sharing. Can you see me now?
Yes, we can.
Okay.
We can see
So
now.
I was talking about Josephson junctions. So you take a conductor, you take another conductor, right? So you have two conductors, my black books. You have an insulator, okay? You take them and put them between the conductors. You take the insulator and put it between the conductors so that you make sure that no current is flowing between the two things. However, we said with quantum mechanics, introduction to quantum computing. Yeah, I think this is it. Let me share. Yep. Just a moment. Let me go back. So we said with quantum mechanics that we have tunneling. And tunneling is a problem because this blue book that I just showed is your barrier, okay? This blue book that I just showed is your barrier. Can you see the book? So this blue book that I just showed is your barrier. And now it becomes a problem. It becomes a problem because electrons can essentially pass through the barrier, okay? However, some engineers have figured out that, wait, this is actually a very, very good way of constructing qubits because you can talk about the state being here or there, and therefore you have superpositions, and therefore you can have quantum bits, you can have quantum qubits, okay? And therefore, this is a way of building a quantum computer, and therefore they use this system. So this is how you do the engineering. I will talk about what you're seeing in the picture. I know you have seen this picture several times. For those of you who are into quantum computing, I'll explain to you what is happening. But essentially, the idea is that you have to have this thing, for this thing to be a quantum circuit, you have to have it at very, very cool temperatures. Otherwise, this superconducting ability disappears and the quantum mechanical ability disappears. So you need a refrigerator. Yes, you need a refrigerator to just cool this system. So the thing you're seeing in the picture is called a dilution refrigerator. A dilution refrigerator. Let me type that in. Dilution refrigerator. A dilution refrigerator. So what it does is that it uses helium to essentially cool the system. And it works very similarly to your refrigerator. It compresses helium to a liquid up there, and then evaporates it. When helium evaporates from being a liquid, it sucks in heat from its environment. So it cools its environment, okay? So up there is usually something like, if I remember correctly, a few thousand Kelvin, the silver parts. The silver parts are usually a few thousand Kelvin. A few hundred Kelvins. So this is a little bit lower than room temperature. And then as you go lower and lower, the thing becomes cooler and cooler until it reaches 1,000 over Kelvin. So very, very cold, even colder than the parts of the universe. So it calls these things by stages. Those of you who want the details of the operation, ask me in the chat. But that's the idea. All these circles that you're seeing are just stages of cooling the system. The circles themselves are not important. They are platforms for these bronze tubes that you're seeing. And these bronze tubes that you're seeing are the things moving around the helium. They are the fridge. They are the engines of the fridge. So it is just a fridge. And you keep it in isolation like this. You don't want any solid near it, anything near it, because all those solids will interfere with the operation of your refrigerator and therefore of your superconducting qubits. Okay? So what are the advantages? Superconducting qubits are fast. They're very quick because you can manipulate these currents very, very quickly, and therefore you can do quantum computing, quantum computation very, very quickly. But the problem is, and this is why you need this, somebody find out for me the cost of a dilution refrigerator. I think it's in the order of millions of dollars. Yes, it's in the order of millions of dollars. You need this expensive cooling system because you need to keep these things at very low temperatures so that they are not interacting with each other and they're not interacting with the environment. And therefore, they are alive as qubits for a very short time, and then very, very quickly, noise is introduced. So they are quick, but they're also quick with noise. This is popular right now. It's used by IBM. I think it's the chief way IBM builds their quantum computers. Google, although Google has other ways, is experimenting with other ways of building quantum computers. But right now, it is popular amongst these two leading companies. And as I'm sure you know, IBM is a leader in quantum computing. Next is trapped ion qubits. Trapped ion qubits. The idea here is a little bit simpler. You have charged particles, okay? And then since they're charged particles, they will react to magnetic fields. For those of you who did physics, I'm reminding you of your usual Faraday's law and Ampere's law. But those of you who didn't do physics, don't worry about these things. But anyway, the idea is that you're able to control these charged particles using magnetic fields, okay? And you're able to essentially use lasers to encode. You basically shine a burst of lasers on these charged particles to encode positive or negative, up or down, and this is essentially how you create your qubits. And then you can do computations that way. By building quantum gates operation, you can hit a particle and put it in a superposition. Therefore, you will have realized a Hadamard state or a Hadamard logical gate. And therefore, you have a superposition and you can carry out other computations on this. Nonetheless, the advantage of these systems, one, high fidelity. Because these things are by definition isolated from the environment, and you're only controlling them using magnetic fields, you're not touching them, okay? You're not touching them physically. They're not like in a physical container, like this container. You're essentially able to carry out, they are able to stay in a quantum superposition for a very, very long time. And this is an advantage. They are more stable than superconducting qubits. However, there's a problem. They're slower. For you to like shine those lasers, and then they hit the charged particles, and then these charged particles also move slower. It means your quantum computing process occurs in the order of seconds rather than in milliseconds, like superconducting qubits. Next is photonic qubits, where you're just using light, okay? So the medium of computation here is a superconductor. The medium of computation here is a charged particle. So a particle with a negative or positive charge. any charged particle. Typically, these are normally heavy ions because heavy ions are more stable. And here it is photonic qubits. So photonic qubits, you are using light. Please mute, please mute, please mute. Photonic. Joseph, please mute. Joseph, please mute. Joseph, please mute. Please mute, Joseph. Thank you. Let's go back. I don't, because these are complicated things, I don't want you to miss anything because of noise. Photonic qubits work using light. The particle of light is called a photon, okay? You've heard of this several times now. A photon is essentially a small particle of light. So the idea is the way you control light, right? Using mirrors, using beam splitters, using all of these things, essentially find a way of controlling photons. You do this by creating very, very precisely made mirrors, precisely made splitters, etc., that can allow you to control individual photons or groups of photons, okay? And you cool these mirrors, these detectors to very, very low temperatures so that they don't introduce noise in the system you're trying to measure, okay? So that is the trick. So there are certain things called polarization. I don't want to get into the details. It's essentially the orientation of a photon. Don't worry about that. And that is the basis of computation here. So you can say the photon can either be oriented this way or that way. And this is my superposition. And therefore, this is my qubit, okay? Once you can realize a superposition, you can realize a qubit. This is very, very good for natural communication. In any case, we are already using optical fiber, and that's why people doing quantum communications, we'll speak about it in a little more detail in a later part of the series, are using photonic qubits to channel information. You just take these photonic qubits, put it in some optimized optical fiber optic cable, and just it passes like that, and it is received on the other end. So quantum photonic qubits are particularly good for quantum communication, okay? And they can be integrated very easily with existing internet infrastructure. So the fiber optic cables, for example, that are in the sea, that bring the internet to Africa. However, for computation, there's a problem of creating two photons interacting with each other without getting together and making one photon. And it's actually very, very rare. It's not very, very rare. It's rare for two photons to interact with each other. It's rare. If I take a torch and I take another torch and I shine them at each other, it is very, very rare for those particles to like come together and make a very intense circle of light here at the center. What is likely to happen is these lights will just pass each other like that, okay? And therefore you have to be extremely clever. You have to be an extremely clever engineer to realize photonic quantum computation because you want your qubits to interact. Why do you want your qubits to interact? You want your qubits to interact because that is the only way you're going to carry out logical operations on the qubits using logical gates, okay? And therefore perform arbitrary computation. I know I've been singing this song a lot, but it is an important song. There are other platforms. We won't get into them because of time. We are almost 15 minutes out, so I'll go through them quickly. Spin qubits use this idea of spin and use magnetic fields to manipulate that. Neutral atoms use tweezers. Tweezers are just very finely focused bits of light that can be used to control an atom. You shine a laser in this direction, shine a laser in that direction. There's an atom here. You can essentially control that atom by controlling your laser. And this is called a tweezer, an optical tweezer. And then there are topological qubits, which I won't get into at all. Forgive me, but you can ask me later on, I'll explain. Now, there's a problem with this system, and hence this dilution refrigerator that you're seeing here. We have said that these things are very sensitive. Anytime somebody, if this thing is carrying out a computation right now, and even I just go to touch it like this, touch it, just touching it causes the entire system to break. Okay, the computation, I have introduced noise into the system. The quantum computer becomes a classical computer, and a very weak classical computer at that. And therefore, I've destroyed the quantum information that I was supposed to use. This is called decoherence. Okay, so any form of environmental disruption, heat, the smallest vibrations, even from me touching it, electromagnetic fields, right? Just light, cosmic rays can destroy any quantum superposition, and therefore it destroys essentially the quantum bits of your computer. For this reason, you need extreme isolation, okay? Isolation means you remove, sometimes they do it in vacuum. Isolation also means isolated even from its own components. So you need to cool it down a lot. So you need to get to near absolute zero, negative 273 degrees Celsius, 0 degree Kelvin. You can't get to zero, but you can get to 0 point something something as they do in the lab. And what does this mean? It means it's an engineering problem. You can see this is a very, very complicated refrigerator, right? It's not your usual refrigerator, and therefore you have an engineering problem and a cost problem. Another way you can solve this is to have something called quantum error correction, okay? Now, what happens is that instead of using one physical system, for example, one atom to represent one qubit, you can use 100 atoms to represent one qubit. And this is the difference between a logical qubit and a physical qubit. So you have one atom that ideally would represent one qubit, but because it is likely to hit something and make a mistake, you make 99 copies of the same thing, such that even if 50 fail, you have 50 that will continue the quantum computation process. And therefore, you will assume that these 100 things represent one logical qubit. And this is very, very important. It's a very, very important fact to put in your mind, that you can have hundreds of physical qubits, but they're doing the computation of only one qubit. So that a few disappear in this stage, a few others survive, a few disappear in this stage, a few others survive. And this is what is called quantum error correction. Okay, so you encode one logical qubit into hundreds or thousands of physical qubits. Google, the company, likes this, their quantum computing division likes this thing called surface codes. Surface codes are just basically you have a surface of a material, and then you take that entire surface and encode just one bit on that surface. So one logical qubit encoded in hundreds or even thousands of surface atoms, okay? There are other ways you can do this. Short codes, I can't remember who did this, and other ways of doing this that allow you to carry out your quantum computing. But I hope you realize that it means your engineering is getting more complicated. So instead of one atom, which you needed to protect from the environment, you have 100. which scales up your engineering. It scales up your dilution refrigerator, it scales up your containers, it scales up your control systems, etc. And this is why quantum computers are very, very large and expensive things. Anyway, we are now in the situation called NISQ, Noisy Intermediate Scale Quantum Computing. So this is considered 50 to 1,000 logical qubits. And then they have errors, but they're showing advantages. So we can already see the engineering advantages, and we will discuss them in detail later on when we're getting closer and closer to engineering and which company is doing what, etc. later on in later part of the series. But in this era, essentially you have noisy qubits, i.e. qubits that are failing, but you are able to still show some advantage. Now, in the next 5 to 10 years, we expect these qubits to continue scaling up. I think IBM expects 1,000 qubits very near. So in the 2030s, we will start seeing commercial scale quantum computers being useful for particular things. They are already starting to be commercial scale. For example, IBM came to the Indaba and were advertising quantum computing cloud facilities, okay? If you have a particularly nasty problem that you would like quantum computers to have a look at, or you're researching quantum software or something like that, quantum algorithms, okay? So anyway, in the near time, we expect to see interesting things like simulation, drug discovery, and optimization. But definitely, post-quantum cryptography. We haven't spoken about quantum communications. We might give it a little bit more detailed treatment, but it is expected that most of the securing system, the cryptographic systems that we're using for our communication will be deprecated in the next 10 years and disallowed in the next 15, okay? By the National Institute of Science and Technology and other international bodies who do these things. They're going to disallow any software that uses these systems, okay? That can be broken by quantum computers. So another place to get into, which we can speak of in a little bit more detail, is quantum communications security as part of this. And in the long term, 10 to 30 years, we expect fault-tolerant quantum computing. In fact, IBM has a roadmap that works towards this. Fault-tolerant quantum computing, meaning that they're very stable, okay? They can be run continuously. They're like a stable large computer, a stable mainframe computer, a stable supercomputer. So this is what we expect in the coming years. And I would like you to start preparing yourself by getting used to quantum mechanics. We agreed that you cannot understand quantum mechanics. Nonetheless, get used to quantum mechanics and quantum computing. The revolution has begun. So thank you very much. I think we have only maybe 5 minutes for questions, and then I have to hand over. We were supposed to stop at 9:30, although we started a little bit late by 10 minutes. So we can have 5 minutes of question, and then I hand over back to Shannon and Dila. Thank you very much. I hope you've enjoyed. I wanted to balance technical and explanation so that you come out learning something new. And I also wanted to make this as accessible as possible. So in case something is not accessible, feel free to raise your hand. I would really love to hear your voices. You feel free to put it in the chats, but I would really love to hear your voices also. Thank you very much. I'll stop sharing.